As you may be aware, not all collisions are created equal. The two main types of collisions are elastic collisions and inelastic collisions, and we will look at each of these separately. An elastic collision occurs when the kinetic energy of a system is conserved. So the total kinetic energy of the system before the collision is the same as the total kinetic energy of the system after the collision. Take an object of mass 1 moving at a velocity of v1, and an object of mass 2 moving at a velocity of v2. The total momentum is equal to the mass times the velocity of the first object, added to the mass times the velocity of the second object. This is before the collision. Because of the measurements involved, we can relate an object's momentum directly to its kinetic energy. So the kinetic energy total before the collision is equal to the kinetic energy of the first object plus the kinetic energy of the second object. If those two objects collide, we will have a change in each individual momentum, but not the total kinetic energy. It will stay the same. The kinetic energy relationship holds true for after the collision as well as before. Perfectly elastic collisions are extremely rare in the macroscopic world. You really have to get down into particle physics before these truly happen. Friction is just too difficult to get rid of in the real world. Bumper cars on an air track with spring bumpers are about as close as you can get. All other collisions result in some sort of energy transfer. Heat, light, sound, these are all forms of energy that are lost from the original system when a collision occurs. These types of collisions are called inelastic. This indicates that there was some type of work being done within the system by some internal force. Consider two blocks of equal mass and move them towards each other at the same speed. The total initial momentum is still the momentum of each block added together. In this case, the velocities are in opposite directions, so the total momentum is equal to 0. After the collision, the two blocks stick together. This is a perfectly inelastic collision. Momentum is conserved, but internal kinetic energy is not. In the example problem, we can assume the ice is a frictionless surface and we do not lose any energy to friction. We have a hockey goalie who has a mass of 70 kilograms, originally at rest, who catches a 0.15 kilogram hockey puck traveling at a velocity of 35 meters per second. The net external forces acting on the puck and the goalie are 0, so we can say that momentum is conserved in this situation. We want to find the initial total momentum by finding the momentum of the goalie and the puck. All the initial momentum is coming from the puck because the goalie is at rest. This initial momentum is equal to the final total momentum. We can consider the goalie and the puck to be stuck together in this case, and so their final velocity will be the same. Substituting for our variables, we end up with a velocity of 0.0748 meters per second. If you think about this situation, that small velocity makes a lot of sense. The goalie is large enough compared to the puck that he's not going to be moving very fast because of the puck's impact. Since the collision was inelastic, we know that kinetic energy was lost during this collision. We can even determine exactly how much. To do this, we must first determine how much kinetic energy there was to start with. Again, the goalie is at rest, so the only kinetic energy initially comes from the puck. We found the velocity of the puck in the problem and the mass of the puck in the problem. So the kinetic energy initially is 1/2 times 0.15 kilograms times 35 meters per second, the quantity squared. This gives us an initial kinetic energy of 91.9 joules. We found the velocity of the entire system after the collision to be 0.0748 meters per second, and the combined mass of the system to be 70.15 kilograms. This gives us a final kinetic energy of 0.196 joules. If we want to know the difference, or how much was lost, we subtract our final from our initial, and we find out that we have lost 91.7 joules of kinetic energy in this system. The things to keep in mind here is that momentum is always conserved in a collision. Energy is also always conserved in a collision, but not necessarily in the same form.